My name is Martin Scott Gordon. This is for a course project of UCSD extension ECE40001. It's embedded hardware design. It's November 27th, 2013 for Professor Donald Thomas. This is my course project. It's a tic-tac-toe game, human versus computer. The problem statement is to construct and implement a human versus computer tic-tac-toe game. This project required the identification of the necessary hardware components, hardware construction, software implementation, software installation, and project validation and verification for the human versus computer tic-tac-toe game. Since this was a human versus computer game, both a human user interface and an artificial intelligence game playing strategy were required for the computer player. A human user interface design was required to allow the human to visualize the progression of the game board as squares are selected by players and to enable square selection within the game board. The computer player employed a game playing strategy to allow offensive and defensive square selection moves. The game of tic-tac-toe is a two-player game where each player takes a turn marking their desired square. The game board is composed of a 3x3 matrix squares where each square can either be marked with the player's mark or empty, indicating the square is available to be marked. Initially, the game board squares are all empty. To win the game, a player must have marked all three squares within a row, column, or diagonal dimension. The game is played with each player marking their chosen squares until a player wins or there is a draw. In the case of the implemented game, the game board is a 3x3 matrix of LEDs. An LED that is not lit by any color indicates the square is available by a player. An LED that is lit green indicates that the square is marked by the human, and an LED that is lit red indicates that the square is marked by the computer. During human square selection, the human can browse through the available squares. As the human browses the available squares, the available LED is lit amber, which indicates that the square may be selected by the human player. To play the game well requires both offensive and defensive square selection. Since one of the players within the game is the computer, the software that selects the computer's move must consider the best choice based on the current squares available. The square selection strategy employed by the computer player consists of the following choices in order from the most to least advantageous. Choose the available square, which results in the immediate win. If the computer has two of the three markings necessary for a win, and the third square is available to mark, choose that available square to win. Choose the available square which results in blocking the opposing player's immediate win. If the opposing player has two of the three markings necessary for a win, and the third square is available to mark, choose that available square to block the opposing player from winning. Choose the available square which results in creating a fork. If the game board has a configuration where the computer selection of an available square results in two dimensions, each having two of the three markings necessary for a win, and the third square is available to mark, choose that available square. During the human's subsequent turn, the human will be forced to mark only one of the immediate computer win dimensions, leaving the computer to win at the next subsequent computer turn. Choose the available square which results in blocking the opponent's fork. If the game board has a configuration where the computer selection of an available square results in eliminating the opponent's opportunity to create a fork during the human's subsequent turn, choose that available square. Choose the available center square. Choose the available opposing corner. If the opposing player has marked one corner and the opposite corner is available, choose that corner. Choose any available corner square. Choose any available side square. Consideration was necessary in selecting a microprocessor that met a number of constraints. The top constraint was that the microprocessor had to run in debug wire mode on the Dragon in AVR Studio. Secondly, the microprocessor had to have enough available GPIO lines for human player-user interaction to drive 18 LED outputs for game board visualization, and one for the potentiometer input and a push-button input for human player square selection. Finally, the microprocessor also needed to have enough program and data memory to support the game program. The ATmega168 fulfilled these constraints and was selected. To facilitate human user interaction intuition, a single tricolor LED was chosen to indicate each game board square. A single LED that can display all necessary colors helped to emulate the square within the game board. Human player game board square browse and selection experience was enhanced with the use of a single potentiometer knob and a single push button. This limited number of inputs reduced confusion that would have occurred with many inputs. The software is driven by a watchdog timer and an analog to digital reading events. Each expiration of the fixed watchdog timer duration results in a possible analog to digital read of the potentiometer, which is used by the human player for game square browsing, a check for pressed push button, which is used by the human player for game square selection, to initiate the computer move choice during the computer's turn, and a check of the game board for a terminal game where a single player wins or there is a draw. The player's turn alternates between the human and the computer until the game terminates. There are three main facets of the software implementation. The first facet is the infrastructure required to track the game board and a player's turn. The second facet is the human player user interaction code that drives the hardware components like lighting of LEDs and reading of the potentiometer and push button. Finally, the third facet is the code required to select the computer player's move. Special consideration was made to abstract the code that drives the hardware components for human player user interaction from the GPIO pins on the microprocessor. This abstraction facilitated a more readable, self-documenting, and maintainable code base that indicate game board action without delving into the details of GPIO pin assignment. This abstraction was performed by managing an array of structures. The array was the 3x3 matrix game board, and the structures were the game squares. Each structure or square contained the GPIO port address, direction address, and pin for square marking, and the state of ownership of said square. Since program memory is limited with small microprocessors, special consideration was made for code reuse. Code reuse was employed to reduce code base by allowing human and computer to call same functions. Code reuse was also used for the computer move selection code for offensive marks and anticipating the need for defensive blocks. Software that implemented computer move selection followed the algorithm delineated within the game strategy section. For software maintenance and reuse, each of the major computer move categories were captured in their own modular function. The biggest challenges within this project were in microprocessor and LED selection and having each calendar time to order and receive the necessary hardware components. The microprocessor was ordered from a vendor on the internet, and the LED was on back order from a local electronics supply warehouse. Back order and shipping times were out of my control and were a risk to meet the schedule for project completion. Until I received the microprocessor LEDs and implemented a small test utility demonstrating their purpose, I was not certain that the previous noted microprocessor constraints were met. Since GPIO lines are limited in small microprocessors, creativity in the user interface played a significant role. My original idea was to have two different color LEDs and a single push button for each square in the game board. This would have required at least 27 or more GPIO pins. The two single color LEDs for each square was not elegant or intuitive for the human user interface. Browsing at a local electronics store, I came across the tricolor LED, which seemed more intuitive, where one LED represents one square. Finally, replacing the individual push button within each square with a single game potentiometer knob that would only light up available squares in a specific browsing color seemed more intuitive for the human interaction experience. This not only improved the human interaction, it reduced the number of GPIO pins required. Being asked to, quote, create a human versus computer tic-tac-toe game, end quote, and allowing the student to find their own solution space, including the debugging platform, hardware, and software, with little other guidance, led me to really place embedding concepts into practice and to mitigate limitations with creativity. Efficient use of the available resources, such as program memory, data memory, GPIO pins, and timers, is probably the best thing I learned designing this project. This is a great lesson to learn from experience and a common thread to all hardware construction and embedded program endeavors. So, just wanted to kind of point out what we have here. So this is the 3x3 game board matrix, and this is the potentiometer that allows you to browse through the different selections. The human player has the takes the first turn. We have the Atmel 168 microprocessor here. We have two breadboards. We have the Atmel Dragon, which is the IDE and debugging for the AVR microprocessor. We're using Linrose tricolor LEDs, as I mentioned before. These are there's resistors, 330 ohm resistors there. This is a potentiometer with a trimmer. This is a push button right here switch, and I'm using a 22 gauge solid wire for the connections. So now I'm just going to go through a few test cases. Again, the human goes first, so I can choose which first position that I want. I'm going to choose this one. And immediately the computer has chosen the center. That follows the strategy that I spoke of with the artificial intelligence. So now I'm going to choose another position. And now the computer has blocked my try to win in the upper row, and now he's set himself up to win in the middle column. I'm gonna let him win and see if he knows that he won, and he takes advantage of that, which he did. So he now has 3 in a row. So he won this game. The computer won. So if I push the button again, it recognized that he won, so it'll start another game. So let's start another one, and I'll be a little bit more sophisticated. This time I'm going to choose the center square. He chose the upper left corner. I'm going to choose the upper right corner, see if I can get a 3 in the row, and I possibly blocked his attempt to get the 1 in the row. So he immediately blocked my attempt for 3 in a row. I'm going to block his attempt for the left column, and he took this spot here. So I'm going to go, let's see, I'm going to go there. So we're at a cat's game, a draw here, because I'm going to choose the last part right here. And so this is a draw. Nobody won this game, and the computer knows it because when I push it again, it resets. So let's do one more. This time I'm going to go lower left. He took the center. I'll take the middle right. He chose the lower right. I'm going to block him. Okay, and he blocked my attempt to get the left column, and I don't see how he can win anywhere, but I'm gonna take this upper left. He blocked my attempts to win there, and now here we have another draw. I've played this 50, 100 times. I've never won the game. It's only resulted in draws. So that's it. That's my course project, Tic-tac-toe game for ECE40001. I hope you learned a little bit and had a good time. Thanks.